Well, so last time we discussed how, or rather we did a comparison on what is it to find the domain of a function. There's actually guidelines, like depending on the function that we are dealing with, rational, logarithmic, radical of even index. And well, why in some cases the function is defined or undefined depending on the value that we plug in. In the same way, we did it for a very simple series to illustrate the idea of finding this interval of convergence. Well, in this case, again, we're not going to plug in every single value of x until we get all the interval of all those values that make a divergent or a convergent series. There has to be a process. And well, once we do the process, there's actually three possibilities. Number one, the series will only converge at its center, x equals to a. It converges for all x, or there's actually a limited interval given by this inequality where r is actually the radius of convergence. So we're going to use the ratio test for all this for all these exercises. So that's actually the process we follow to determine the interval of convergence, somewhat the domain of the function represented by the power series. Well, it's just a fancy name, it's just another name. We call it the interval of convergence. Well, so let's do the ratio test. So that's limit n approaches infinity, a sub n plus 1 over a sub n. And well, so when we do the ratio test, we write down limit. Okay, so the original series shifted by n plus 1. That is, whatever you see the letter n, replace with an n plus 1. So that's limit absolute value of n plus 1 x plus 2 to x plus 2 to the n plus 1 divided by 3 to the n plus 1, which is going to be 3 to the n plus 2. Well, when we did the ratio test, what we did is to divide by the original rule. But remember how weird that quotient looked like? So in this case, I'm going to skip that step, and instead of dividing by a sub n, I'm just going to go straight to the multiplication by the reciprocal of this, which is 3 to the n plus 1 over n times x plus 2 to the n power as n approaches infinity. And well, so let's do all the algebra, all the required algebra to simplify this expression as much as possible. Number one, limit n approaches infinity, absolute value n plus 1. This x plus 2 to the n plus 1, I'm going to write it as x plus 2 to the n times x plus 2 to the first power. The denominator 3 to the n plus 2, I'm going to write it as 3 to the n times 3 to the second power, which ultimately is the number 9. For the next factor, for the other factor, that's simply 3 to the n plus 1, which is 3 to the n times 3, and n times x plus 2 to the n power. Alright, so let's divide out factors. We can divide out x plus 2 to the n, x plus 2 to the n. We can divide out the 3 to the n with the 3 to the n. And that's going to leave us with, well, we can also divide 9 with 3. That's 1 and 3. And that's going to leave us with the following limit. Limit n approaches infinity, absolute value of n plus 1 times x plus 2 over 3. Alright, is there anything over 3n actually? Okay, so let's observe this limit right here. Notice this limit contains two different variables, x and y. I mean x and n. So in this case, we need to compute the limit only for n, because that's what the symbol below the limit notation it's indicating. So the dummy variable here is n. I know it's kind of weird because usually the letter x is the one used for variables most of the times. All right. So this is what we're going to do. I'm going to take out of the limit everything that doesn't contain an n. Actually, that's going to be this part right here, the 3 in the denominator, and the x plus 2. However, that x plus 2, I'm going to take it out along with its absolute value bars, because in this case, well, x can be pretty much anything. And if it's negative, for example, well, we are talking about a radius of convergence. And that radius of convergence is supposed to be a positive number. So depending on the value of x, we may need these absolute value bars to make sure it ends up being a positive value. So that's times the limit n plus 1 over n as n approaches infinity. And while computing this limit, polynomial over polynomial, degrees of the polynomial, they match. The limit is 1. So what do we have? Absolute value of x plus 2 over 3 times 1, which is absolute value of x plus 2 over 3. Well, so that's our final answer for now. What are we going to do with this final answer? Well, so we want to find the interval of convergence. Okay? Well, we're using the ratio test. Let's go back and review the ratio test. For the ratio test, the series converges whenever the limit is less than 1, diverges whenever the limit is greater than 1, and it's inconclusive whenever the limit equals exactly 1. Alright? So, because we want to find the interval of convergence, we have to set this absolute value of x plus 2 within a condition that gives us some convergence. Well, in other words, need to set this less than 1. That's in order to force this quantity to converge. Because, well, that's what we want to know, interval of convergence. Why would we want to know the interval of divergence? That is, I mean, the interval where it blows up to infinity. Well, we don't want to know that, right? Well, I'm going to take this inequality on the side. That's the absolute value of x plus 2. And over 3, less than 1. I'm going to multiply both sides by 3. That's going to be the absolute value of x plus 2 less than 3. And writing this absolute value inequality as a compound inequality, that's going to be x plus 2 less than 3 and also greater than negative 3. Right? That's how we solve this kind of inequality, this kind of absolute value inequalities. Keep solving the inequality. Subtracting 2 on the 3 sides. That's going to be x greater than negative 5 and x less than 1. Well, what is that going to represent? So number 1, the original series, that x plus 2, that's indicating that the series is centered at negative 2 actually. So at negative 2, that's the center of the series. That means the values that we will plug in to the original series and that will output a convergent series will vary. So center at negative 2, but with the distance of 3 units away from that center, that is. So number 1, let's highlight this value. So isolating the absolute value in the inequality, this number right here, it's going to tell us that the radius r equals to 3. The radius equals to 3. Alright? So, and well, so 3 units away from negative 2, that's going to be 1, 2, and 3. That's the 1, the upper endpoint, and 1, 2, 3. That's negative 2 minus 3. That's negative 5. All right? Yes.
So, should the final answer be inequality or 4A?
So the fact that it's inequality, well, that means we get a positive and an absolute value it's that we get a positive and a negative because it's the same distance on either direction, in the positive direction or the negative direction. So now that we got the endpoints of the interval, so from this inequality, so now that we find the endpoints, the lower endpoint and the upper endpoint, we are going to have 4 possibilities. Number 1 possibility is, okay, this -5 to 1 with these inequality signs means -5 to 1 exclusive on both endpoints. Another possibility is -5 to 1 both inclusive and inclusive on the lower endpoint, and inclusive on the upper endpoint, or the reverse, inclusive on the lower endpoint, exclusive in the upper endpoint. So we need to figure out which of these 4 answers is going to be. And in order to do that, we need to test the endpoints -5 and 1 in the original series right here, in a similar way that we did in the class before about testing, substituting values of x. And for some values we got a convergent series, for some values we got a divergent series, so we're going to do the same here. So in a way, what we did last time to plug in some values it was to prepare you guys for this part. So test x equals to -5. Alright, so sigma n equals 1 to infinity. That's an n times -5 plus 2 to the n over 3 to the n plus 1. Substitute, replace x with -5. Simplify the series. Now this series will no longer contain x, so it's no longer a power series. It's a series of terms, like like an algebraic series like the ones that we did in the previous sections. So no more x, so that's n -3 to the n over 3n plus 1, and the factor in the numerator, -3 to the n, is the same as saying inside of the parentheses -1 times 3 to the n, which is the same as -1 to the n, 3 to the n. Okay, we're gonna do this, we're gonna need this later. I'm gonna do this only once. Later I'm just gonna go with the answer. So that's sigma n equals 1 to infinity, so that's -1 to the n and 3 to the n over 3 to the n times 3. 3 to the n plus 1 is 3 to the n times 3 to the first, which is 3. Well, let's keep dividing out any common factors to simplify all this. So we're going to obtain this series. Sigma n equals 1 to infinity of -1 to the n over 3. Alright, so let's forget about the power series, the series that contains the x, and let's focus on this new series. So for this series, we will use any of the 10 techniques that we learned to determine convergence or divergence of a series. Well, I think this first factor is going to give us a hint of which series is going to be a good one. Question?
For the sigma, shouldn't it be n equals 0 because the original problem at the bottom of it has 0?
It had a 0. Well, actually, it doesn't matter. So, well, let's change it to a 0. That's fine. Thank you. Everything is still going to be the same anyway. So, well, in this case, we're going to use the alternating series to determine the convergence or divergence of that series because, well, we have an alternating factor. All right. So there's 2 conditions that we need to check for the alternating series. Number 1, that the limit of the sequence b sub n without the alternating factor has to be equal to 0 in order to proceed to the next condition, which is to check that the sequence is decreasing. However, in this case, infinity over 3, this is infinity and it's not a 0. Well, that means that it's divergent by the alternating, by AST. That's alternating series test. All right. So in this case, because plugging in x equals to -5, that gave us a divergent series. Well, that number -5 should be excluded from the interval of convergence. So right away we can cross out two of the possibilities. So I can cross out the two possibilities that involve the -5 as inclusive. So now we need to check whether the series would be convergent for the upper endpoint x equals to 1. So test x equals to 1. That is sigma n equals 0 to infinity n times 1 plus 2 to the n over 3 to the n plus 1, where x gets replaced with 1. So that's going to give us sigma n equals 0 to infinity n times 3 to the n over 3 to the n times 3 to the first. Again, I'm writing this rewriting it using laws of exponents. And 3 to the n cancel with 3 to the n. That's going to leave us with the following series. That is sigma n equals 0 to infinity n over 3, which is similar to the series we ended up in the previous test. However, this series doesn't have that alternating factor, so we're not going to use the alternating series test to test that series for convergence or divergence. So we need to find another one. Number one, it looks like a geometric because of the quotient, but it's not a geometric because it's not a number to the n power. Yes, there is an n, but it's not a power. It's definitely not a p-series because we don't have the n in the denominator to a power n. It's not what else? It's not. Definitely the integral test can be used because, well, number one, it's positive, that is true. However, it's also continuous. However, it's not decreasing, it's actually 1/3 n. That's like a straight line with a positive slope of 1/3. So in this case, well, ratio test or root test is going to be inconclusive. I can see that already. So in this case, we're going to use the n-term test. So for the n-term test, for divergence, all we have to do is take the limit of the sequence at n equals as n approaches infinity, and we need to make sure that the limit is not 0. Well, in this case, the limit is not 0, so because it's infinity, so diverges by n-term test. All right, diverges by n-term test. All right. So, well, because in this case, for the upper endpoint, we also got a divergent series. Well, we can cross out one of the possibilities, which in this case is the one that includes the 1. So really, the interval of convergence does not include the endpoints. Question?
Is it necessary to check them through the series, or can we plug it back into x plus 2 is greater than 30? And see that the absolute value of x plus 2 is greater than 3.
Well, if we set it like greater than 3, that'll give us the interval of divergence, but we don't want the interval of divergence, we want the interval of convergence. So that's why, well, I listed the conditions for the ratio test. So less than 1 would give us the convergence, greater than 1 would give us divergence, right? So we want the interval of convergence. So that's why we force it to converge by setting it less than 1, all right?
So we're looking for it to be less than 3. Can we just plug it in right there? We have for -5 to 1.
From -5 to 1. Well, yes, we get the endpoints of the inequality, but we still need to test them for convergence or divergence because, again, we can have 4 possible case scenarios in which both endpoints are exclusive, both endpoints are inclusive, or one of the endpoints is inclusive, the other one is exclusive. So that's why we do all these tests. You will see the difference in the next example. All right? All right, so sigma n equals 1 to infinity and -3 to the n, x to the n. over the square root of n plus 1. All right. Limit n approaches infinity of absolute value of negative 3 to the n plus 1 x to the n plus 1 over the square root of n plus 1, which is n plus 2, times, well, instead of writing the division by the original term, I'm just going to multiply by the reciprocal, that is the square root of n plus 1 over negative 3 to the n x to the n. All right. So let's do all the necessary algebra to simplify this. So number 1, I'm going to write this negative 3 to the n times to the n plus 1 as a limit n approaches infinity. That's negative 3 to the n times negative 3 to the first power, which is just negative 3, x to the n times x to the first, or x, and divided by the square root of n plus 2 times the square root of n plus 1 over negative 3 to the n x to the n. Well, so let's divide out some factors. We can already divide out the negative 3 to the n's. We can divide out the x to the n's. And I think that's about it for now. So that's going to leave us with the following. Limit n approaches infinity, absolute value of negative 3 x square root of n plus 1 over the s square root of n plus 2. All right. So again, this limit is a limit in terms of n, not in terms of x. So everything else we can take it outside of the limit. So number 1, absolute value of negative 3 will be positive 3. Absolute value of x, it's absolute value of x, because x can be anything. So, and because we're finding a radius of convergence first, that radius is supposed to be a positive quantity. So because that means it's going to go into one direction or the other direction. That doesn't mean negative. So it's still a positive value, however, using a sense of direction in this case. Limit n approaches infinity of the square root of n plus 1 over the square root of n plus 2. However, how about we write everything in terms of one single radical? N plus 1 over n plus 2. Well, this limit right here will be, so if we introduce the limit symbol inside of the radical, which I think it would be easier, notice how we have polynomial over polynomial, both degrees match. They're both degree 1, which can just go with the ratio of the leading coefficients, which is the square root of 1 over 1, and that's 3 absolute value of x. Square root of 1 over 1, that's the same as saying the square root of 1, which is 1, which reduces to 3 absolute value of x. So that's our final answer for the limit. But because we want to determine convergence in this case, we need to set this less than 1. That's our condition for convergence, right? Because we want the interval of convergence. Well, let me take this inequality on the side, divide both sides by 3 to get absolute value of x less than 1/3. So from this, after isolating the absolute value term, whatever number we're left on the right hand side of the inequality, that's our radius of convergence in this case. And our radius of convergence is r equals to 1/3. Well, let's keep solving this inequality. Absolute value of x less than 1, that means x less than 1/3, I mean not 1, less than 1/3, and greater than negative 1/3. So that's going to be our interval of convergence. Well, so if we draw a number line, that's 0 right here, and negative 1/3, 1/3. That is, 1/3 units to the right or to the left. That means every number in between -1/3 and 1/3 that we plug into the power series will for sure give us a convergent series. However, it is yet to be determined whether even the endpoints -1/3 and +1/3 are also part of the of that set of values that make a convergent series. So we will find that out. That means we will have potentially 4 results, 4 answers. Exclusive for both, inclusive for both, exclusive, inclusive, inclusive, exclusive. All right, one of those 4 intervals will be the actual one. How are we going to know? Well, we need to test both endpoints right here. All right, so test x equals to -1/3. All right, so we're going to go back to the original series and test sigma n equals 1 to infinity. That's -3 to the n times -1/3 to the n, which is the number we will plug in, square root of n plus 1. -1/3. All right. What about this -1/3 to the n? That's the same as saying the following. Sigma n equals 1 to infinity, -3 to the n, 1 over -3 to the n, divided by the square root of n plus 1. Well, so in this case, we can divide out the -3's to the n, and that's going to leave us with a whole new series to test. Sigma n equals 1 to infinity, 1 over the square root of n plus 1. So let's look at this series. This new series, for this new series, we need to use one of the 10 tests. Well, I mean, it looks like the integral test would be a good candidate. It's it's positive, it's continuous, and it's decreasing by just looking at the expression, but that's going to take a long time. So, however, how about we use a comparison test? Because if we neglect that one, this series looks like sigma n equals 1 to infinity, 1 over the square root of n, which is 1 over n to the 1/2, and this series is a p-series, and in fact it's a divergent. It's a divergent p-series. So we're going to use a comparison test. If actually, well, there's 2 comparison tests. Number 1, there's the direct comparison test, which is usually the shortest test, or the limit comparison test. So here is the issue here with the direct comparison test. For divergence, we need to show that huge is greater than or equal to big. Well, in this case, is 1 over the square root of n plus 1 greater than 1 over the square root of n? So the test fails, but lucky for us, we have a plan B. And that plan B is the limit comparison test. That's limit of the original series, the ratio of the original series to the test series. And that's, well, dividing by a fraction is the same as multiplying by the reciprocal. And that's limit n approaching infinity, square root of n over the square root of n plus 1. Well, we can group this into one single radical, like we did before. Well, again, polynomial over polynomial, the degrees match. we can go with the ratio of the leading coefficients. This is really the square root of 1 over 1, which is the square root of 1, which is 1. Well, we don't care about the numerical result, just part of the, just its properties. Number 1, this is positive and it's also finite. So this series right here will do whatever the test series does, which in this case is diverge, because for the lower endpoint of the interval of convergence we got a divergent series. Well, so we can already cross out two of the possibilities, these two that include the lower endpoint in our interval of convergence. So testing the upper endpoint will be critical to determine which of these two will be the actual final answer. So let's find out what it is. So let's test x equals to 1/3. So testing x equals to 1/3, that's sigma n equals 1 to infinity, -3 to the n, 1 over 3 to the n, and over the square root of n plus 1. Well, sigma n equals 1 to infinity, that's -3. Well, actually I'm going to rewrite this -3 to the n as -1 to the n times 3 to the n, and 1 over 3 to the whole thing to the n power is 1 over 3 to the n over the square root of n plus 1. Alright, so we can divide out some of the factors. Sigma n equals 1 to infinity, -1 to the n, 1 over the square root of n plus 1. Alright, so let's have a look at this whole new series. Okay, so I think it's clear about what test we're going to use, which in this case is the alternating series test. That's because we have an alternating factor in our series. So the alternating series test, for the alternating series test rather, we need to check two conditions. That one condition is number 1, that the limit n approaches infinity of 1 over the square root of n plus 1, that is the limit of the sequence without the alternating factor has to converge to 0, and in fact it is, because that's 1 over the square root of infinity plus 1. Well, that's still infinity in the denominator, divide by infinity, the limit is 0. So the first condition is satisfied. The second condition is that the sequence without the alternating factor is decreasing, and we show that by showing this inequality right here. That's 1 over the square root of n plus 1 plus 1, which is n plus 2. Is that less than or equal to the square root of n plus 1? Is that inequality true?
Yes.
It is, because the denominator on the left hand side is going to be a larger number, giving us as an end result a smaller number, and indeed that checks the sign of the inequality. Well, what does that mean? This series then converges?
Absolutely.
Not absolutely, just converges, because I haven't taken the absolute value of the series. So converges by alternating series test. So it doesn't matter if it doesn't converge absolutely. Convergence is convergence. Well, so going back to the 4 possibilities, well, actually we crossed out 2 out of them. So that means we are going to cross out one more, the one that excludes the 1/3, right? And that's because the 1/3, the positive 1/3, gave us a convergent series, so that it's included in the endpoint of in the upper endpoint of the infinite series, on the power series. Yes.
Are we not including x equals -1/3?
Because
Why did it diverge then?
okay, because well, we substituted x equals to -1/3. That gave us this series right here, which we analyzed, and it turned out being a divergent series.
But then we did the limit comparison test?
Yes, well, for what that means, so when the limit is positive and finite, this series will do exactly whatever the test series does, which in this case it's to diverge. So if the test series diverges, well, then the original series also diverges, right? So that's why we got exclusive for this. And in fact, how about we erased these ones and let's erase the whole thing, and the actual interval of convergence is exclusive here but inclusive here, negative 1/3, positive 1/3. All right, so again, there are cases like the previous case gave us both endpoints diverging, that is exclude them from the interval of convergence, but in this case we got exclusive and inclusive. Okay, all right, let's look at one more example. We're gonna have time for only one more. So, well, the first two cases, the first two examples that we did were examples in which we end up with an actual radius of convergence. You know, it's actually the third situation. Now we're going to look at one example in which converges only at its center, and then the last example is going to be as an example in which the series converges for all x. Well, you'll see how that works. Well, for now, let's look at the limit using the ratio test. That's n plus 1 factorial x to the n plus 1 over n factorial times x to the n. That is the original term, the n term shifted by 1 divided by the nth term. In this case, I didn't do the multiplication by the reciprocal because we didn't have a quotient term. So let's simplify this. N plus 1 factorial divided by n factorial. So let's simplify this so we don't have any factorials. That is limit expand over the largest factorial, n plus 1, and times n factorial, because that matches the n factorial in the denominator, x to the n times x to the n, actually x to the n times x to the n, x to the n factorial, and approaches infinity, and close the absolute value bars. Well, so that's going to leave us with the following. Limit absolute value n plus 1 times x, and in this case, is this the one? Yes. And approaches infinity. But again, first of all, we are evaluating a limit in terms of n, not in terms of x. Let's take that x outside. Absolute value of x, limit n approaches infinity of n plus 1. But what's this limit equal to? Infinity. Well, usually I would just write, so here is the thing. The textbook, if you read the textbook, will only tell you, when the limit is infinity, the radius is 0. When the limit is 0, the radius is infinity. But it doesn't really explain why. I'm going to explain why is that, and I'm going to explain it in a way that it's not a legal way to explain it. Let's put it in those words. So, okay, so this is infinity, right? Well, infinity times any value of x, it's still going to be infinity. But well, if we try to compare infinity, is infinity less than 1? Never. So that's why the radius is 0. But did that make sense? Why is that 0? That's kind of weird. Well, I'm going to explain it in a different way. I'm going to take this inequality, absolute value of x times infinity, less than 1. And well, here, the weird thing is I'm going to keep still solving the inequality as if infinity it's an actual number like 3 or 5. And here is where it's the incorrect thing to do. I cannot treat infinity to divide both sides by infinity because, well, we don't know which infinity is bigger, and we cannot set a condition to say, hey, these two infinities are the same. No, because we don't know how big infinity is. Well, cancel the infinities, which is technically weird. That's the illegal part. And this means absolute value of x is less than what's 1 over infinity? 0. That's why the radius is 0 when the limit is infinity. Alright? I know, technically I explained this in an illegal way, in a way that we're not supposed to do math with infinity, but you know, mean justifies the end in the end, right? So, yes.
Wouldn't it be less than or equal to 0?
No, less than only. Because the condition for the ratio test, which I listed over here, is converges for the limit less than 1, diverges for the limit greater than 1, and inconclusive for limit equal to 0.
What's 0 times infinity?
0 times infinity is 0. So when it's 0 times infinity, that'll give us 0 less than 1. And in that case, it's true for all value of x. That's going to be the next example, which we will discuss next time. So in the meantime, well, let's call this number 1. This means r equals to 0. Well, so illustrating this as an interval, if the series in this case it's centered at 0, well, we're not going to have an upper endpoint nor a lower endpoint like the previous examples, because, well, if we're centered at 0, if we move 0 units to the left or 0 units to the right, we're not moving anywhere, right? We're just steady at the center, which is 0. So this means converges only at its center, x equals 0. Try any number. Test your favorite number, like -1, plug it in here, +1, plug it in here. You will get a divergent series, and it will only converge for x equals 0. Let's plug in x equals 0 and see what happens. So sigma n equals 0 to infinity and factorial 0 to the n. Well, what's 0 to the n? Isn't that just 0?
Yeah.
Even if you keep the 0 there, expand the series. 1 factorial times 0 to the first power plus 2 factorial times 0 to the second power plus 3 factorial times 0 to the third power plus ... What is that equal to? 0 plus 0 plus 0. What's that? Does that mean diverge or converge? Well, it's weird. The sum is equal to 0. It's equal to nothing, but it's converging. It's converging, and it only converges at the center x equals to 0.